So I believe we will wait about 1 or 2 more minutes and then we will get started. But this is our 9th and final session of ROSES 2021. We're going to be giving an introduction to machine learning from seismologists with Omkar Ranadive. And before we get started, I would like to acknowledge that ROSES this year has been supported by a number of organizations. So we would like to acknowledge several organizations for both financial and in-kind support. So thank you to the Seismological Society of America, the seismology section of the American Geophysical Union, and in particular, support from the section president, Suzanne Vanderlee, support from the Alaska Satellite Facility, and support from IRIS, the Incorporated Research Institutions for Seismology. We're very grateful for all of their support, and ROSES this year would not have been possible without them, as well as several of my co-organizers for the summer. So thank you again to Dr. Suzanne Vanderlee and to Liam Tony, Anant Hariharan, Sydney Dybing, and Nate Stevens, who have all assisted with coordination for the summer. Okay, so our lecture today will be given by Omkar Ranadive. Omkar currently works as an applied scientist at Alkera Labs. Prior to this position, Omkar obtained a Master's of Science in Computer Science from Northwestern University, where he worked on machine learning related to seismology with Suzanne Vanderlee, and he comes highly recommended to give this overview of machine learning for seismology. So I think with that, I will let Omkar begin his lecture. As always, feel free to ask questions in the Q&A, and we will do our best to get through the questions as he works through his lecture.
So hi, I'm Omkar. I guess let's just get started with the lecture. So we are essentially going to be divided into two main parts. So in the beginning, we will go over the basics of machine learning, how a machine learning workflow is. And in the second half, we will be mostly focusing on neural networks. So in a machine learning workflow, the first step is always to gather data. And this step is not really, you shouldn't rush over this step, right? So because we need to always define our problem well when we are gathering the data instead of just rushing and collecting any kind of data. So let's try to do this with an example. Let's say we want to predict the P delay times. So if we want to make a model which predicts P delay times, then we want to gather data which would be relevant and which would be relevant to predicting those. So for example, that would be, we would need to collect something like the latitude and the longitude coordinates of the earthquake, the stations, and the depth of the earthquake, the ray path parameters. So essentially, when collecting data, make sure that you know what you want to predict at the output and collect data in such a way that it's a good description of the problem. I would also like to talk a bit about machine learning terminology. So when we talk about data in machine learning, we always represent it with the variable X. And while collecting data, we also collect something called as output labels with respect to the data. So in this example, which we are talking about, the variable X or the data will be those features which we collect, that as the latitude and the longitude coordinates, the ray path parameters, the depth of the earthquake. And Y would be the output labels, which are the actual P delay times, right? So in the machine learning problem, what we essentially have is a tuple of X comma Y. And this is what we will be passing on forward into our workflow. Okay, so this is again, which you will commonly see in pretty much every machine learning problem, that when after collecting the data set, we split it into a train and test set. So the idea behind that is that we don't want to train our model on the entire data. And why is that? Because we want to make sure that our model is learning to generalize and not learning to memorize. So how do we do that? Basically, we can decide the split, but we split most of the data into training set, let's say 80-20, and we will leave some for testing. So the idea is that by leaving some data for testing, and that's the data which the model hasn't been trained on, or the data which the model hasn't seen. So if it ends up performing well on both training and testing, then we can say that the model has generalized well. But on the other case, if we have a scenario where it is performing really well on the training data, but not that well on the testing data, then it's a problem. So that's why this split is pretty important in any machine learning problem, to make sure that it is generalizing. So once we split the data into train and test, then we are supposed to choose an algorithm and train the model using the training data. And at the same time, we test how well it generalizes using the testing data. So what exactly is this model, right? So this model is basically just a set of parameters which will get tweaked such that it tries to predict the problem at hand. So again, going with the example which we had for the P delay times, the model could be something similar to a tomographic model, right? Because in a tomographic model, the parameters can be used to predict the P delay times. So similarly, there would be some set of parameters which would be tweaked and learned to help us predict those P delay times. Okay, so just going a little bit more over that. So when we talk about data in context of ML, it essentially means something which should be a good descriptor of whatever we are trying to model. And these data samples are made up of features. So just like that P delay example, another simple general example, let's say we are having this problem of predicting house prices. So for this, what would be the good features for a data? That would be the size of the house, locality, maybe number of bedrooms and bathrooms, and so on. The main idea being that you need to be careful while collecting the data. Don't just go and collect anything. So define the problem well and accordingly collect it. So this is called as features. And like I said, with our data, in most problems, we have an output label associated with them. So that data sample is essentially a tuple of X, Y. And again, going with some terminology, whenever we have these output labels available to us, it's called as supervised learning. Why? Because we are essentially providing supervision to our problem, right? And there is another class of machine learning where if we don't have these output labels. So for example, in case of P delay times, we did not have actual P delay time values, or in case of this house price prediction, we did not have the actual house prices. Then that would have been the case of unsupervised learning. And we won't really be going more into that, but the idea is that we still try to apply some machine learning to it based on the patterns present in the data. But we'll be more focused on the supervised learning aspect of it. Okay. So going deeper into that workflow, which we just saw. So essentially, like I said, the model is something which is made up of parameters. And like to simply put, when I say a model learns something, all it really means is that the model is learning some function f such that given some input x, it's going to learn to predict an output y. So remember, in our problem, we are passing it a tuple of x, y, right? Where x are the features and y is the output label provided. So based on that, it will learn this function f. And so it basically just learns to map that input x to y. In simple terms, that's what a machine learning model is. It is a function approximator. Okay, again, going deeper into this. So what would a function look like? So let's look at an extremely basic example over here. So I'm sure most of you are familiar with this equation. This is the equation of linear regression, right? So you must have seen it in terms of y is equal to mx plus c. So similarly, instead of m and c, we use the ML terms, we call them weights. So that would be W1 and W0, which are essentially the slope and the y-intercept. And in a machine learning problem, we are going to have such weights which are going to be learned, right? And so even a linear regression model is essentially a machine learning model, because we have certain weights which we will learn, which basically means we end up learning some function and learn to map some x to some y. Okay, so this same idea can be extended further to multiple parameters. We can have multiple features, which again, features are defined by the variable x in terms of machine learning. So if we have 3 features, that would be x1, x2, x3, and we can define weights for these features, which are going to be learned by the model. So one way of looking at this is that these weights are essentially weighing those features, right? So for example, let's say for a P delay problem, the depth of the earthquake maybe is an important feature, then let's say that's feature X2, then it would, if it's an important feature, the model will learn to give it higher weightage. So that would be represented by having a higher weight value over here. And similarly, if it's some feature is not that important, it would have a lower weight value. But the idea is still pretty straightforward. We have some features X, we take the dot product of that with some weight vectors, which we are going to randomly initialize first, and which will get tweaked such that we learn to predict a good output Y. Okay, so how are these parameters learned, right? So I'm talking about that we are learning to tweak these features, we are learning to predict a good output Y, but how do we go about doing that? So in ML, we do that by defining some loss function. Now comparing this to seismology, this is similar to a misfit function. And over here, you can see again, it's the same terminology over here. So we are going to have some observed label values, which we are going to collect during a gathering of the data phase. And then we try to reduce the loss of that with whatever our model is predicting. That's the predicted label values. So if you look at that regression problem, the mean squared error loss is a commonly used one. But basically, we can use any loss as long as we are trying to reduce that difference between whatever is whatever is observed and whatever we are trying to predict. So putting everything together. So again, like going through all of that workflow, what we essentially do in any machine learning problem is gather data X, gather labels Y. We're going to define a model, which can be any model parameterized by some set of weights. And then we also define a loss function like that mean squared error loss function. And then we start by randomly initializing this weight parameters, which we are later on going to tweak such that we try to reduce the loss. And then we keep on doing this until the loss is pretty much reduced to a good extent. So any questions till this point? Okay. So basically, I think what is clear till now is that a machine learning model is learning a function based on some parameters W, and we want to tweak those parameters W such that that loss is reduced, right? So the question which arises right now is how to actually update those parameters W such that the loss L is reduced. And in most of machine learning problems, this is basically done using gradient descent. So what this basically is that we have some loss function and we have a loss landscape associated with that loss function parameterized by our weight parameters. So basically for some weight values, we are going to get some loss, and that will end up, you can show that that ends up somewhere in this loss landscape. Now, when we take the gradient of that with respect to those parameters, what we get is the direction of steepest ascent, or the direction in which the loss increases the fastest. So the negative of that gives us the direction of steepest descent, and that's essentially what gradient descent is. And why do we want to do this? We essentially, by moving in this direction which this gradient descent points to, we want to go into these areas of minima, because these areas basically signify that we are going to end up reducing our loss. And by going to these areas of minima, we essentially mean we tweak those weight parameters in that direction pointed by the gradient descent. So a few things which I want you all to notice over here. You can see that this loss landscape is non-convex, right? So that's an important thing to know. So we don't just deal with linear models in machine learning. There are non-linear models which try to model highly complex problems. So most of the loss landscape are going to be non-convex like this. And we are going to try to somehow navigate this and try to find these minimas to get a good enough approximation. But then the question might arise that if our loss landscape is going to be non-convex like this, can we ideally reach a global minima like this? Because even if it's non-convex, there should be one global minima, right? And ideally, we would want to reach this point. So can we guarantee that a machine learning model can end up reaching over here? So the answer to that question is no. We can't guarantee that we end up reaching a global minima like this. But the idea is that it doesn't really matter that much as long as we reach a good enough point. So what I mean by that, if you look at this, this is the ideal solution which we want to reach at, but you can't really guarantee that because it's a highly non-convex problem. So even a good enough solution like this minima is fine. So, and that's usually something which is much more doable if we have lots of data, if we tweak the parameters enough. So yeah, just the takeaway from this is that you can't guarantee to reach the optimum solution in a machine learning problem, but in most cases, it won't matter as long as we reach a good enough approximation. Okay, so like the main takeaway from all of this is that a machine learning model is basically learning a function. Other way of looking at it is given some training data, we are learning the distribution of the training data, and we do that by minimizing the loss on it. That's how do we do that? By tweaking the parameters using gradient descent. So that's like the main takeaway over. That's all, most of what basically all machine learning models. But there is some important note which I want to talk about over here, that we can only predict well on new data if that new data is following the training distribution. So just because a model is performing well, we can't just use it anywhere. So I would like to say that with an example. So let's say again with that P delay example, we collected a lot of data for P delay times which were recorded at the continent. We trained our model on it. It is performing great. But then if we try to use the same model to predict P delay times at the bottom of the ocean, it's not going to work well, right? Why? Because the data distribution at the bottom of the ocean is this different, because the characteristics of the data over there would be different. So just keep that in mind whenever dealing with machine learning problems, is that a model will perform well only if those distributions match. Okay, so any questions? Okay, so then again, there are, like I would say, two major classes of machine learning. One is traditional machine learning, where we have things like regression, logistic regression. But the newer class is neural networks, which has become really famous in recent times. And so we really want to focus on this part over here. And I would like to just say that most of this stuff is not really recent. All of this has been present since the 90s, but the neural networks has recently gained so much traction. That's because now we have a lot of more data available. So we are going to go now into neural networks, and you will see that they still follow the same principle which we looked at till now. That is, a model is nothing but something which learns a function based on some parameters W. Okay. So let's get into neural networks, because they are what is the most famous right now. So what makes neural networks so special, right, and much better than a traditional machine learning models, is that they have this property that they are universal function approximators. What that means is that they can learn any function, even if it's some complex nonlinear function. So it can learn any mapping f of x gives y. But there's an asterisk behind it. Obviously, that's dependent on the fact that we have enough training data. We have a big enough model to actually work on the data. And important thing, it won't learn the function perfectly. It just approximates it. So it's a function approximator, but they are really powerful because it can practically learn any function. And the second huge advantage of a neural network model is that these can be trained end to end. What does that mean? So in a traditional analytical workflow, what we would usually do is we build up different modules, right? And then we have different modules where we want to process data differently, do something else. So it's a lot of coding, a lot of modules, and that takes time. But in neural network, we can eliminate all of that. We just take our data, pass it through a model, get some output at the end, and train everything end to end. So it's a pretty straightforward and a hands-off approach, which is what makes neural networks so powerful. Okay, so the most common type of a neural network is a fully connected network. So let's look at what that is essentially. So in that so these circles which you are seeing in ML terminology, they are called as nodes on neurons. And at that input, these are nothing but the features which we have defined. So that's the data which we'll be passing through. And this is called as a fully connected network because every node is connected to every other node in the next layer. So if you see this node over here is connected to every node in that next layer. Similarly, this node over here is connected to every node in the next layer, and this goes on forward. That's why it's fully connected. And in this, what we are essentially learning is these connections. So each of these lines or the connection will have a weight matrix associated with it. So it's that same idea which we have seen previously. We have weight matrices associated with each of them, and then we just end up learning those weights. Some more ML terminology which I want to talk about is that that initial layer is always called as an input layer. The thing which we get at the end is what we call as an output layer, where we'll get our label prediction. And everything in between is what we call as hidden layers, because it's hidden between the input and the output layer. So some of you may have also heard of this term called as deep neural networks. So that basically term comes from the fact that if you have many such hidden layers which are stacked between the input and the output layer, that network is a deep network. So all networks like fully connected network, convolution neural networks, and other different types come under a deep neural network. So just some terminology out there. Okay, now let's look at this model in a little bit more depth. So like I said, these are the input nodes. And I said that each of these connections are going to have some weight associated with it, right? So what's happening at every node in the next layer is basically this. So let's just focus on this node for now. So we have some input over here. We again do the same thing which we have been doing till now. We take the dot product of that with some weight matrix. We have some input x2. We take the dot product of that with some weight. We have some input x3. We take the dot product of that with some weight. Then we combine them and then we get this z1 over here. So this equation is pretty much the same as what we saw before, right? And then after that, what we are going to do is we are going to pass it through a non-linear function. So these are very important. Why? Basically, if we just keep on doing this stuff over here, that multiply the weight and the x vector, then it's just a linear model, right? And even if we do it at multiple layers, that's just a linear combination of some linear equations. But if you want your model to learn some complex non-linear functions, you need to have non-linearity in your data. So these non-linear functions are called as activation functions. And these are some of the ones which are commonly used. So you don't really need to know the exact form of these functions for now, but just know that these are non-linear functions and they are used to introduce a non-linearity in the model. So basically what we do is at each of these nodes over here, we are going to have an activation function. So we pass this input which we just got through an activation function like this, and then that is passed on forward to every node in the next layer. So this output A1 acts as essentially as the input at this point. So that's the feature at this point over here. Similarly, we will have an A2 over here and A3 over here and an A4 over here. So for this node, for example, instead of this X1, what we are going to have is an A1. Instead of X2, we are going to have an A2 and so on. So is that clear? Any questions till this point?
It doesn't look like we have any questions.
Okay, good. So moving on. So one more intuitive way of looking at this is that, like I said, these non-linearities are very important. So they, in a way, they transform our data and project it to a higher space. So what I mean by that is, remember that we have multiple neurons over here with multiple weight matrices, which we are then passing through some non-linear function and adding them all up ahead, right? And we keep on doing this in subsequent layers. So that is essentially similar to like increasing the dimension. So you are transforming your data such that it becomes more separable in higher dimensions. So that's kind of what this neural network model is doing, running transformations on the data such that it becomes more separable. Okay, so whenever we talk about neural networks model, there are essentially two passes that we need to look into. So first is called as the forward propagation, which is similar to the forward modeling used in seismology. And so in this, what we essentially do is we just calculate the values in the forward direction and then get that output label at the end. And by that, all I mean, we have weight vectors, we have our input data, take the dot product, calculate the activation, pass that thing forward, and keep on doing this till you get some output label. And then that entire principles remain the same. Once we get that output, we are going to have some loss defined. Based on that loss and the output which we have, we calculate the loss, and then we are going to apply gradient descent just like we did in the previous slides. So that process of applying gradient descent is what is known as backward propagation. And again, to compare with seismology, that would be similar to inverse modeling. And over here, the idea is it's backward propagation is basically just a form of gradient descent. So to put it like to just have a gist of it, it's gradient descent with chain rule of derivatives. So we will start by calculating the gradient at the output layer. Then we calculate the gradient at this layer. We take the chain rule and pass both those derivatives back to the previous layers and so on. So that way, all the model parameters or the weight vectors W are tweaked with respect to that loss. And that's how a model ends up learning. So one more thing I think I would like to add at this point is that you can see why a lot of data is required for neural network models, right? Because you can see as compared to those traditional ML models, we have a lot more weight parameters over here. Plus we have non-linearity in between. So that loss landscape for such a complex model is going to be very complex. It's going to be highly non-convex. So to actually learn something, we require lots of data on it. But if you have lots of data, these models end up performing really well. Okay. So I think at this point, I'm basically saying that fully connected networks are universal function approximators, right? So if they can learn anything, then why do we even need other architectures like convolution neural network? Can't we just use this simple idea and apply it to every single problem? So let's look at that as why other architectures are needed. Okay. So before looking at why other architectures are needed, I think let's see what happens if we directly use this fully connected networks we just talked about for some other kind of data like images. Now let's say, for example, we are trying to build a classifier which predicts whether an image is a bird or not. And if we have an image like this of size 500 by 500, then what do we define as features in this case? We can define, let's say, the pixel values as features, right? So if we do that, then that would mean there are 250,000 pixels because the image is of the size 500 by 500. And each of this pixel value will act as an input. And now assume that at this first layer, there are 100 such nodes, right? And remember, this is a fully connected network, right? So if we have 250,000 inputs and 100 nodes in the first hidden layer, then the weights, this connections which we will have would be 25 million. Why? Because that would essentially, each of those pixels would be connected to 100 nodes in the next layer. So you can see that's a big problem. So this is essentially a weight explosion over here, right? So if you have such a huge set of weights, then your model is just going to end up overfitting and not actually learn to generalize. So what I mean by that is assume that you have, let's say, 10,000 images and you have 25 million weights. So if you only have 10,000 images and so many connections, then your model will learn to memorize that training data completely. But if you then test it on some new images of birds, it won't perform as well. So the problem over here is that for most of the interesting real world problems, like which involves data like images and signals, it's difficult to define good features, right? So, and if we use things like the pixel values as features, we can't really pass it directly through a fully connected network because it won't end up working well because of this weight explosion. So how do we go about solving this? So first approach is similar to the traditional analytical things which we have been doing since forever. And that is to manually extract features, build some modules to process this in some way, and then apply some analysis on it. But that is again the same time consuming process, and we don't really want that. We want the learning to be end to end. So the second approach is to understand the principle that any kind of data is going to have some characteristics associated with it. So an image data has certain characteristics. Similarly, signal data has certain characteristics. So we can build our model architectures in such a way that we end up leveraging those characteristics. So let's look at what characteristic an image data may have. So thing to note over here, if you're building a bird classifier, then what a bird actually has is a beak, right? So every bird has a beak. And so that's a pattern. And to actually detect whether it's a bird or not, we mostly need to just focus on whether it has a beak or not. We don't really care much about all that background information. Second thing which you should notice are these patterns, like for example, the beak over here will be present in different parts of the image for different images of bird. But because it's still a beak, we should ideally be able to recognize that it's a beak based on just some same set of weights. But remember, in that fully connected framework, each of the pixel was getting assigned to a different weight value, right? Because it was a different connection. And that doesn't make sense because both of them are a beak. So we should be able to detect them using some same set of parameters instead of having different weight parameters for them. Okay, I think there's a question. So can each node in each layer be processed separately? That is, can the processing at each layer be parallelized to the number of nodes? So ideally, you don't want to process it separately because we want that learning to be end to end, and these neurons end up becoming interdependent on each other in a way. So so basically, they don't essentially learn the way we humans do it. A neuron may learn to extract some part of information, and that information is dependent on something extracted by other neurons and so on. So does that answer it, or any more questions? Okay.
That does answer the question. Thank you.
The only two personnel that should be downrange would be John Tome and myself.
Okay. How do I get this box? Just let me get the chat box out of the way. Okay. So moving on from over here. So again, so coming back to this, what we are basically claiming is that raw data like this has certain characteristics which we can leverage. So the first characteristic which we saw, that there are patterns in image data. So we should be able to detect them using same set of parameters. Secondly, we can see that subsampling the image won't change the object. So if we have a big image, make it into a smaller image, it's still an image and we can recognize what's happening in it. So you can reduce the size of the image or extract some useful information for the image, and still that would be good enough. So we don't really need all of the data present in an image. That's the second property. So, okay, I think there's another question. So is there any rule of thumb to estimate the number of data needed for training a neural network? So not really, but basically what you want to do is make sure that the data which you have is not lower than the number of weight parameters which you have in the model, right? Because otherwise, like I said, it will just end up memorizing it all. So, and instead of seeing one way of looking at whether we are actually generalizing is to divide our data into those training and testing sets. Because if our model is performing well, both on the training data and the testing data, then you can pretty much say that it's doing well and actually generalizing and not just memorizing. Okay, so at this point, I just want to look at this. So remember, so initially what we tried to do was take this input image and pass this directly through a fully connected network. We saw that it did not work. So now what a convolution neural network essentially is doing is it's leveraging those properties of images. So we add these additional layers in between, which leverage those properties of image, and then see that we are still doing having a fully connected network at the end. But now instead of passing those huge set of features, we will extract useful information and only pass that useful information forward through our fully connected network. And now the problem becomes much more tractable. Okay. So we'll just go through now what these layers actually do. So the first layer is the convolution layer. And this essentially takes advantage of those two things which I just talked about with respect to images, right? So there are patterns in an image like that beak of a bird, which we can take advantage of. These patterns appear in different regions, so we can develop same set of parameters to detect them. And so in ML terminology, we call these things filters or kernels. So the idea of filters is nothing new. It has been over here since forever. But in the past, these filters were hand designed to hand engineer the features. So I just want to show an example over here. So in the past, if you want to, let's say, do edge detection like this, then you can design a filter like this over here. And this is again also called as a kernel. And so how do you detect edges using a filter like this? Is let's say you apply this to this patch over here. So the idea is that each of this numeric value will be multiplied by the pixel value on which you place it on. So it's a 1-to-1 mapping. So we multiply this 1 with some pixel value we place it on. We multiply the 0 with some other pixel value we place it on. You do that multiplication, you add everything up and take the absolute value of that. So if you do this on this patch, the absolute value will be close to 0, right? Why? Because all the pixel values over here are of the same color. So they are going to have the same or similar value. So the multiplication of ones and minus ones and then summing that up will lead to an absolute value close to 0. On the other hand, if you, let's say, do it over here, so you can see that the pixel values over here are different from the pixel values over here. So now if you multiply that, do that 1-to-1 multiplication and sum it up, the absolute value is going to be a large number. So that way you can detect whether it's an edge or not. But the thing is, so again, we have been doing this since a long time, but in the past, all of this had to be hand engineered. So we had to design these filters ourselves. So it took a lot of time and it was required domain expertise, right? But now a convolution neural network will find these filters by itself. So that's the cool thing about it. So we don't need to manually assign values over here, just randomly initialize them. So you can think of each of these values as weights, the same thing which we talked about till now. So these are weights which we randomly initialize, and the model will tweak them itself to extract meaningful information from our data. So again, how do we do that? It's the exact same idea. We are going to have some loss at the end, apply gradient descent such that the weight parameters are tweaked to extract relevant information to reduce that loss. So that is what makes a model like convolution neural network so powerful. You don't need to define features at all. It will learn to extract meaningful information from the data by itself. Okay. So now let's just look deeper into how exactly these kernels are applied. So think of this as an image, right? Because an image is nothing but a set of numeric values. And so, like I said, we define these filters and we are going to initialize them randomly. And also remember that we want to initialize multiple such filters. The assumption over here is that each filter will learn to extract something else. So yeah, and these will be learned by the network. So let's just run through an example and see what happens. So we have this filter over here. So we are going to place it over our image. And like I talked about before, what we do is a 1-to-1 multiplication and then sum it up. So for example, if we place this filter on top of this one gets multiplied with this one. Similarly, this one gets multiplied with this one. These minus ones over here get multiplied with the zeros over here. So if you do that, and if you sum up everything, what we are going to get is sum of these three ones, right? That is a 3. Then you can move forward. And again, another machine learning terminology, you will see something called as strides. So a stride of 1 says that you move forward by 1 column. So previously it was over here. We just move forward by 1 column. And then we repeat the process, place this filter again on top of the data which we have over here, start multiplying. And you can see in this case, this -1 gets multiplied with this one. This -1 gets multiplied with this one. So that's -2. Then this one gets multiplied with this one. So that's -2 plus 1, which gives us a value of -1. And keep on doing that across the image. So similarly, if we had a stride of 2, we would have moved forward by 2 columns, as you can see, and that would have given us a different value. So that's a parameter which we decide ourselves while building these models. Okay, so now what I want to see over here is that, okay, we are going to keep on doing this. We get some values. And like I said, what I'm claiming is that this convolution operation is helping us extract patterns in the data, right? So let's look at if it's actually able to do so. So this is an image, and we can see that one pattern over here is the set of diagonal ones over here. So was our filter able to extract it? So if you see, we were able to extract it, and we were able to encode that information of the diagonal 1 in form of this numeric value 3. And the cool thing over here is we were able to do that using that same single filter. We were able to extract patterns in different parts of an image using a same single filter. So now we are basically leveraging the information available in the image. So same ideas, there would be some other filter which would do the same process, build up this feature map, and we do this for all the filter matrices which we have. So once we get that feature map, then we are going to move forward. So yeah, again, so what I want to show over here, if we had considered that fully connected network problem, you saw that every pixel value was connected to every node, which wasn't ideal. But now if we are using it in the form of filters, this value 3 is only dependent on the 9 values over here, right? So takeaway being, now it's not fully connected, only connected to 9 inputs. So there are far fewer parameters, which improves learning. Okay, so that's the first part, which is a convolution layer, which helped us extract those patterns. Then second, I talked about we can keep on making our image smaller while retaining useful information. So that is what the max pooling layer is used for. So this was the feature map which we extracted from that convolution operation, right? So now what? And again, I want to say that max pooling is not applied on the input image itself, but on some representation of the image, because this feature map is also essentially some representation of the image. So what a max pool operation is doing is within some defined small square, we just end up choosing the maximum value. So within this square, we will choose the value 3. Within this, we will choose the value 0, and so on. So the idea again, why do we want to do this? Because remember, we want to reduce the number of parameters or the information which we are passing forward. So we just want to keep the most relevant information. And this is in a way keeping the sharpest features, right? We are just keeping the maximum value, which tells us about the sharpest features. And it's in the form of summary statistic. Okay. And then step number 3. So after passing through this convolution layer, the max pooling layer, we have now reduced that image to some small set of values. Take those set of values, flatten them out, and now pass it through a fully connected network. So instead of those 250,000 pixels, we now have some small set of values which we can pass through a fully connected network and learn on it. So now the problem becomes much more tractable. So now just looking at everything again, convolution neural network, all it is doing, it's leveraging information of images to extract relevant stuff, and then we pass it through a fully connected network. Okay, any questions with any of this? Okay. So how do we use this in seismology? So one straightforward way of using this is that if you can gather images in seismology where the patterns are clearly visible in images, then you can directly apply this idea of 2D convolutions to extract information. And a good rule of thumb would be that if humans can identify it and classify it, a model certainly can, given enough data. But what if we only have signals? So that still works, right? So this entire thing which I talked about with respect to images, the idea still remains true, even if we talk about with respect to signals. We still have patterns in the signals which we can detect using 1D convolutions instead. So instead of that 2D kernel, now we have a 1D kernel, which we will pass through our signal, extract patterns through it. And that way we can make our model predict different things. Like we can help it learn to detect an earthquake by extracting useful information from it. And in the lab, we are going to try to work with images and both signal data to see how to actually do this in practice. Okay, so that was convolution neural networks. Main takeaway, we don't want to directly use fully connected networks. Why? Because in most of the data, it's difficult to gather features correctly. So leverage the properties of that data and develop architectures which leverage those properties for us and do an end-to-end training using that architecture. So similar to a convolution neural network, which is great at detecting patterns, we have another form of neural network, which is called as a recurrent neural network. And so the architecture of a recurrent net is designed to work well on sequential data. So example of sequential data is we have, let's say, sentences, right? Because in that, every word is dependent on the words which come before that. Or we have, when I'm talking, the speech which I'm giving is dependent on the speech which I've given till now. Similarly, in signal data in seismology, there may be that the exact sequence of events may be of interest. So this architecture over here is designed to work well in that case. Let's see how this architecture works. Okay, so it's called again a recurrent net. Why? Because we are essentially unlooping this same thing over here. And now the inputs are basically time steps. So if this was a signal, then the value at each time step would be the input. And this A over here is basically any neural network. It can be a fully connected network or convolution neural network or whatever. Idea is still kind of similar. We have some input, we pass it through that network which we have defined over here, and then we can produce some output at each time step. But that is again dependent on the problem. So do we want to produce output at each time step, or do we want to produce output at the end? So that is problem dependent. So we need not generate output at every time step. It depends on the problem. And so what's till now, it's pretty similar, right? So what's the new thing in this is use these arrows which you see over here. So that is in a way the memory of the network. So at after extracting information at every time step, we encode that information and pass it forward to the next time step. So basically this value x1, this model A over here is getting the value x1 as well as the information from the previous time step. Similarly, this x2 is getting information from the current time step x2 plus the encoded information from x0 and x1, which goes forward. So that is how we pass on the sequential information. And even though, so this architecture is a bit different, right? But again, the idea is still the same. So all of these are nothing but some weight parameters. We're going to have some loss at the end. You run gradient descent on that such that the weight parameters are updated in a way where we try to minimize the loss. So it's the same update rule no matter which model architecture we are using. It's just that these different model architectures work with different kinds of data. Okay, so that's what I was talking about. The core idea always remains the same no matter what we use. So what should you be using for seismology? So that basically depends on the problem. If what you want to do is detect patterns in the data, you could use convolution neural networks. If what you want to do is, if you think that that sequential information is somehow going to be important, then you could use an RNN, or you could combine both architectures to use both the ideas together. So there are different ways of mixing and matching these kind of architectures. Okay. Okay, I think there's a question. What does encoding the information before passing it to the next step mean? So essentially, that's just that will just be some output of the neural network model at this step. So that A is going to produce some output, And so, and an encoded information means just some numeric value. So output produced by a neural network model, which we pass on forward. And the idea is that because it's based on some neural network model, when we end up tweaking those parameters, it will end up passing useful information forward, because that useful information is going to be relevant to reducing the loss at the end. Okay, so any other questions before we move forward? Okay, now let's look at some applications. So first, I want to talk about Earthquake Detective, which was a project which I did at Northwestern. And in this, essentially what Earthquake Detective is, it's an online crowdsourcing platform on Zooniverse. And so over here, we have over 6,000 volunteers, and we upload data and we make them classify those waveforms. So the volunteers can classify the data in one of the 4 types, which is earthquake, tremor, noise, or none of the above. And so the data which we uploaded was a specific kind of data. So we only uploaded data from potentially triggered seismic events. And so why are these potentially triggered seismic events of interest to us is because so first of all, what are potentially triggered seismic events? So whenever a large remote earthquake happens somewhere in the world, those strong seismic waves which are caused by that earthquake could trigger some local seismic events all around the world. Now, these potentially triggered seismic events are of interest and are difficult because they generate low amplitude, then they have lower bandwidth. And so typically in seismology, we have a template of data, template signals, which we can use to detect signals, right? But for these potentially triggered events, there isn't a large enough database available. And these signals, again, are lower in amplitude, so they get easily buried in noise. So that makes it an interesting problem from the machine learning standpoint also. So what we did, first of all, was we gathered a lot of such kind of data. We uploaded it to our Earthquake Detective platform on Zooniverse, and then we made the volunteers classify it. So the reasons that the volunteers were able to classify it is because the way we present the data to them. So they get presented the data in the form of images as well as in sped up audio version of it. So in quite a lot of the images, you can clearly see the distinguishing characteristics between each of the earthquake, noise, and the tremor types. And that audio version is also has some pretty good distinguishing characteristics. Like an earthquake, that spike in an earthquake is going to sound like a slamming of a door. A tremor signal sounds like a train is moving over a railway track. So because of these characteristics, these volunteers who weren't experts were still able to classify the data pretty well. And the good thing is, now that we have crowdsourced our classification and we have a data set available, we use that to now train a machine learning model on it. This was the model architecture which we used. And I think the main thing which I want you all to notice again is that this is still following the same ideas which I've discussed till now. So we had 2 kinds of data available. One, we had the images as well as the signal data. So we ended up using both of them. So first part is the image data. So we had 3 channel plots, which were plots from the BHZ, the BHE, and the BHN channel. And so we pass it through this convolution architecture, which we have talked about till now, extract relevant information for it. Similarly, we had the signal data, which we pass it through something called as wavelet scattering transform. And this is essentially a form of convolution. It's like an hierarchical convolution. Idea is still similar. From that signal data, extract meaningful patterns and features which we can later on use. So what I want you all to see is it's still the same idea that we have a lot of data in the beginning. We apply specific architectures over it, extract useful information, combine that, and then pass it through a fully connected network. So no matter what kind of architecture you see, they will generally follow this principle. So that's what we did, and it ended up performing pretty well. Okay. So that's one of our papers. And second, I want to talk about something called as earthquake transformer, which is a pretty recent paper. So in this, this was the architecture which they used. Now this looks pretty big and intimidating, but just ignore these things for now. So what this model is actually doing, it's predicting 3 things simultaneously. So it predicts the arrival time for P phase, the arrival time for the S phase, and actually detects whether it's an earthquake or not. So now let's look at these things over here. So you can see there are lots of layers over here, but if you like look deeper into it, it's nothing but convolutions, and LSTMs are a form of recurrent neural networks. Again, more convolutions. So the point is, this is big, but all it is really doing is just combining all those ideas which we talked about, stack all those multiple layers so that it can learn many complex things. So one new idea which they added was this thing about transformers. So it's a pretty new thing in machine learning that you teach your models to attend to specific parts of the information. So what that we'll see in a second what that looks like. But what you all to take away from this thing over here is that everything is end to end. No hand engineering is required, and this is just a mix and match of everything that we have studied till now. The core principles remain the same no matter what architecture which we are choosing. So looking at the attention thing over here, so this kind of a neural network model learns to attend to useful information. So for example, like I said, in this problem, they did a 3-way prediction, right? They were predicting the arrival time for P waves, S waves, as well as detecting whether it's an earthquake or not. So for detection, the model learns to attend to this part of the signal. For P wave prediction, it learns to attend to this part of the signal. For S wave, it learns to attend to this part of the signal, which is pretty cool, right? Because again, we did not provide it or teach it that you need to attend to this part. It just learned it on its own based on this entire framework. So that's, I guess, pretty interesting that it can actually learn to attend to useful information just like we humans do it. So any questions till this point? Okay.
Doesn't look like we have any questions. I think you're okay to continue.
Okay. So one other project which I want to talk about is on wildfire detection, which we are currently doing at my company. So this is about, I think you all know that there are a lot of wildfires happening, especially in California. So can we build a machine learning system to detect it before it gets out of hand? And so that's one of the major projects which we're doing over here. This has an interesting background because the way we do this is we have these wildfire cameras placed all around California. And so this has an interesting history because it began as a collaboration between the Nevada Seismological Lab and the Forest Guard team. And again, it was for the purpose of detecting wildfires. But in the initial days, they just had a camera and they had manual people looking through it. But currently, it has grown into a big network with a lot of partners, and it is spread throughout California and some other parts. So, okay. I think there's something in chat, so I'm just gonna. What type of P or S transformer can detect? Can it discriminate between PG and PN? So I think in that paper, they did not had that kind of discrimination, but if you can collect enough data where you have actually classified between PG and PN, then you can make your model do the same. Okay. Okay, so coming back to this problem, so the data which we are getting in this problem is from the cameras which are present or placed throughout the forest areas. This is what it looks like. And so ideally for wildfire detection, we want to detect before everything catches on fire, right? So what we ideally want to do is smoke detection. So you can see images like this where we have smoke coming out. So for our model, we build this bounding box around the smoke so that it learns to detect this kind of smoke in our model. So combining everything together. So essentially what we are doing in this case, we have some image data coming in through those alert wildfire cameras. Then we have our AI model, which continuously takes in those images and detects whether there's a smoke or there's no smoke coming out. If a smoke is detected, we confirm it with a human and then we alert the authorities. This has actually worked well quite a few times, that we were able to successfully detect smoke and prevent a wildfire from spreading. But I think what I want you all to understand over here is that behind the scenes, this model is also still a form of convolution neural network, because we have images, we apply some of the same principles which I talked about. So we can apply these same architectures over different array of problems, which is, I think, what makes ML really powerful. Okay, so concluding the lecture with that, I think machine learning is a really powerful tool because it's extremely general and it can learn the characteristics of different kinds of data. And as we saw over here, you can use similar kinds of architecture to solve everything from geophysics problem to problems of detecting wildfires and all different kinds of things. And this has been, in recent times, it's pretty much been used for all kinds of things, from detecting protein folding problems to genetics to particle physics to even in geophysics. There are many interesting papers these days. I definitely think this machine learning can be used to expedite the scientific development process. So I hope you all also would get more involved in this and try testing out machine learning a bit more. So that is it with the lecture. So any questions with anything which we have talked?
Doesn't look like we have any questions. So I think if you're ready, we could probably move into the lab section.
Okay, yeah, we can do that. Okay, so for the lab, I have shared a Google Colab link. So I've shared a Google Colab link with you all, and so you can just go over here, save a copy of that to your own drive, and then run it if you want to edit it. So in this lab, essentially what we will be working on with is this library called as PyTorch, which is used for doing all these computations which we just talked about. So it's divided into 3 activities. First is just introduction to PyTorch. All I want you all to see over here is that PyTorch is basically very similar to NumPy. The main difference being that you can use PyTorch on a GPU, which speeds up the training process by a lot. So just a few basic things over here, go through the things which I've written over here. So you can see that the functions are pretty similar to what NumPy functions are. And it's also very easy to convert arrays from NumPy to PyTorch and back from PyTorch to NumPy. So yeah, some basic functions over here to get you all used to how the torch modules work. Then in activity 2, what we're going to do is predict earthquake arrival time based on the station location and earthquake location. This is basically taken from the unit 7, which you have already done. So in that, just to revise what we did back in unit 7, we wanted to predict the arrival time based on some function t, which was dependent on the station locations and the earthquake location and some velocity model which we defined. Right, and then we had defined a misfit function, which again, now after the ML lecture, I think you can understand it's pretty much similar to a loss function. And what we wanted to do, we tried to reduce the loss between the observed values and the values which we are trying to predict. And so the model which we used to generate the observed values was this homogeneous velocity model. So now for this activity, what we are going to do, and what I want to again show is that this is a non-linear model, right? So I wanted to show that a neural network is capable of learning such non-linear models. So we generate the synthetic data similar to the way we did in the unit 7 using this homogeneous velocity model. And then we define a neural network model and try to predict and see if our model actually ends up learning an equation like this. So I've divided this into the steps which had kind of described in class. So it's the same workflow which we talked about during the lecture. So yeah, so instead of gathering data, we will be synthetically generating it for this problem. convert it to PyTorch, and just go through the things I've written over here. So essentially, just go quickly through what we have done. In PyTorch, you can see it's pretty much similar to defining a PyTorch model is similar to defining a class in Python. So you do the same thing as you would do for defining classes in Python. You just inherit this torch.nn module, and then you need to have these two functions. So inside the init function, you define what kind of model architecture you want. So if we want to design, let's say, this simple fully connected network with 4 inputs and 8 hidden units, so you can do it in this way. So it's a one line function. So you do nn.linear 4,8 for signifying that we are having 4 inputs and then 8 hidden units in between. And after that, we only have one single output, which is we are predicting the arrival time. So for this one output, we then simply do 8,1. So you can see in terms of code, it's really easy to define these models. And then once we define the structure of our model, the actual processing is done within the forward function. Remember from the lecture, what we essentially do is take that data, pass it through each layer, and also apply non-linearity after passing it through a layer. So we pass that data, incoming data X, through this first FC1, which was this thing over here. And then we apply the ReLU non-linearity. So ReLU is just a non-linear function. We get some output, we pass it through the final layer, and we return X. So a very simple model, just to get used to how to build machine learning models. Then again, defining loss is also straightforward. PyTorch already has predefined losses, so you can just call them directly. And so this is the L1 loss, which is basically similar to the misfit function defined above. Then in step 2, we always initialize these model parameters randomly. So we don't need to manually do anything, just initialize the instance of this class. The PyTorch will automatically define or initialize the weight vectors for us. And in machine learning models or machine learning problems, we have something called as a learning rate. So this controls essentially how fast we are learning, right? So whenever we calculate the gradient with respect to a loss, now we want to update the parameters with respect to that, right? So depending on whether the value of this learning rate is high, so if it's large, then the values of the parameters would be updated rapidly. If it's low, if it's too low, it would be updated slowly. So there's a trade-off between that, because if we keep it too fast or too high, then you might end up skipping those minimas which we talked about. But if you keep it too low, that training process could be too slow. So it's an hyperparameter. So this needs to be manually decided for a problem, which can only be done by tweaking around with it. And then there's another thing for a machine learning problem, we define something called an optimizer. So this is essentially what performs that gradient descent for us with some optimization. So one of the most commonly used ones is an Adam optimizer. So for those interested in reading more, you can go through that link. So third step, like I said, calculate the loss with respect to those parameters, and then we update the parameters. In terms of code, you can see it's extremely simple. So it's just one for loop. So this was the model which we defined over here, right? So we just pass our data through it. And because it is inheriting the PyTorch class, it will run this forward function by itself. So just by doing this model X, it runs this forward function, calculates the output and returns it to us. Once we get that output, which is a prediction, we use our loss function, calculate the loss, and then we are going to calculate the gradients. So while using PyTorch, remember to always run this optimizer.0grad thing. Why? Because we want to calculate the gradient with respect to the current loss, right? But in PyTorch, the default behavior is to store all the gradients we have calculated till now. So this ensures that we only calculate the gradient with respect to the current loss. And then that complex process of calculating the gradient, passing it through backwards to the chain rule of derivatives, in terms of code, it's just this one single function. That's loss.backward. That's it. So you can see in terms of code, it's extremely simple to build such models. So just build this, and like I said, in machine learning, we want to decrease the loss function. So you train the model, you can see that the loss decreases, and just we are gonna see some of the values. You can see that it's learning to predict pretty well. So the values predicted are close to the actual generated values, which was pretty nice because remember these values were created using a nonlinear function. So even such a simple model was able to learn that nonlinear function. And then, yeah, in this bonus activity, like I talked about that learning rate thing. So just try tweaking the learning rate and see what happens to the loss, if it's actually learning it properly or not. In the next activity, we are going to use data from Earthquake Detective. So in this, we just train on images directly. So you can, the data gets downloaded and this is what the data looks like. So an earthquake it's pretty straightforward, and noise looks like this. And then you're going to use convolution neural networks for this. So same idea, convert it to NumPy array, from NumPy convert it to torch. And then remember I talked about that ideally you should split between train and test. So that's what we are doing over here, splitting the data between train test. And now we want to implement an architecture like this. So you can see that the core still remains the same. You define a class with an init function, a forward function, and all those complicated convolution operations which we saw are pretty simple in terms of code. You just define nn.conv2d. So where do these numbers come from, right? So this number 3 is the input. Why? Because we have a 3-channel data from the BHZ, the BHE, and the BHN channel. So it's grayscale and 3-channel, as in it has 3 images. So that's why we had this 3 in input. And everything else you see over here, it's an hyperparameter which we need to decide ourselves. So what I mean by that, so the value 8 over here signifies that I'm going to have 8 filter matrices. You could have kept it to 16, you could have kept it to 4. It depends. You just have to play around with the parameters. Second, that kernel size is the filter size. So what size of the patch do we want to apply over our image? So a 5x5 would be a 5x5 filter. And I already talked about what strides are in the image. And again, so even though there is no thumb rule to decide what the exact values are, the general trend which you can basically follow is that initially in an image, the data is going to be highly correlated, right? So what you can do is keep higher strides and a bigger kernel size. As you move forward, the data gets more correlated because we are only extracting relevant info from it. So start reducing the kernel size, start reducing the number of strides. And similarly, you can see that we are applying max pooling operation after every convolution layer to just keep the sharpest features. But important takeaway again, these values, there's no actual way of determining them. So we just have to play around with parameters. So what I would suggest whenever you are solving an actual problem, look up and see, look at existing models which have solved similar problems and see what kind of parameters they have used and try to move from there. The next thing which I want to talk about is, remember this step. So this step of convolution layer and max pooling layer is done using these functions. And then we are supposed to flatten out our data and then pass it through this fully connected network. So this number which I used over here, 3264, comes after extracting information and flattening out the data. So obviously it's based on a mathematical formula which you can manually calculate. But while building these models, what I would recommend is to just have a print statement after this flattening step. And once you've built this, just quickly run it for a single pass. Right? What I mean by that is don't train it, but you have your data X, run it through that, and just see what the shape is. So this would come to your number of samples, 3264. So if it comes to that, then we know how that this is supposed to be 3264. So that's how I decide this value over here. So that's a quick way of doing it. But otherwise it's the same thing. Then in the forward function, again, pass it through convolution, add a nonlinearity, pass it through a pooling layer, add a nonlinearity, and so on. And the order of operations is preserved over here, by the way. So it works in the exact same way. And again, so the rest of the code is pretty much the same as the previous activity. You define a loss function. This time we use cross entropy loss. So you can look it up over here, what it means. But basically it's a commonly used loss for classification problems. Define learning rate, define your optimizer. And this again, the actual code is just one for loop. right? Predict something, have your loss, calculate the gradients, and you're going to learn something and see the train and test accuracy. And again, so the output will be different for each of you because the parameters are going to be randomly initialized. So it's okay if the output varies a bit. You can try running multiple instances of it and see how much it varies. Also try tweaking the parameters if you want. And finally, this activity is something which you all be doing yourself. In this, instead of the image data, we directly use the signal data from the Stanford earthquake detective data, from the Stanford earthquake data set. So the main difference over here is now instead of 2D convolutions, we are going to use 1D convolutions. So I have already processed the data for you all, but then you should build a model similar to this thing which you've seen over here. Main difference being instead of conv 2D, you will be using conv 1D, and values you can play around with it. Just try to get some good accuracy. And then I will post the solution later on. But that's about it. So again, any questions with anything? Okay.
Okay, are we waiting for any final questions?
Yeah, otherwise it's done. I think is there one? How many hyperparameters are being used? So the hyperparameters for our model is just the learning rate. And all you can technically call the things which you define. Well, let me just share my screen again. So anything that you have to manually define is what you call an hyperparameter. So let's say for this image classification problem, we had to define these values ourselves. So that's in the way a hyperparameter. Then we had to define the learning rate over here. That's an hyperparameter. But yeah, you have to manually tweak them based on the problem. Okay, any other questions?
Okay, well, I think with that, we will end our session for today. Thank you so much for all of your time and for putting together the lecture and the lab exercise. And thanks to our participants for viewing.
Okay, bye. I will be online if there are any other questions.
Perfect, thank you.